All right, let's talk about one of the most classic experiments in all of chemistry, the electrolysis of copper sulfate. Now, it's a super important practical, but let's be honest, anyone who's tried it knows it can be, well, a little tricky. So today we're going to crack this thing wide open and make it all crystal clear.
And hey, don't just take my word for it. As chemistry teacher Paul Roberts says, this is one of the toughest practicals for getting good, clean results. But you know what? That's exactly why we're tackling it head on. Once you understand what's really going on, you can totally master it.
So here's our game plan for today. First, we are going to absolutely nail the setup. Then we're going to look at two really different scenarios, one with inert electrodes that just kind of sit there, and another with active ones that actually jump into the reaction. And then we'll bring it all home, compare the results, and see what it all really means.
Okay, first things first, the setup. Honestly, getting good results in this experiment is all about building a solid circuit from the start. If you get this part right, everything else just falls into place. So what even is electrolysis? At its heart, it's just about using electricity as a tool. We're sending in a direct current to force a chemical reaction that wouldn't happen otherwise. In our case, to break down that copper sulfate solution. Right, let's build this thing. We start with our DC power supply. We'll run a wire from the positive side through an ammeter so we can measure the current, and then to our positive electrode. Then from the negative side, the wire goes through a variable resistor, which is crucial for controlling the current, and then finally to our negative electrode. Simple as that.
Let's get our terms locked in. The anode is the positive terminal. An easy way to remember this is a little acronym, an OX. It stands for anode is for oxidation. And oxidation, well, that's just a fancy way of saying something is losing electrons. And its partner is the cathode, which is the negative terminal. This is where reduction happens. So to complete our little memory trick, just think red cat. Reduction happens at the cathode. So anode, positive oxidation, cathode, negative reduction. Got it? Awesome.
All right, let's dive into our first case. We're going to use inert graphite rods for our electrodes. Now, inert is the key word here. It means these rods provide a surface, a stage for the reaction to happen on, but they don't actually get involved themselves. They're just neutral observers. So we dip our graphite rods into that bright blue copper sulfate solution, we flick the switch, and turn on the power. What do we actually see happen? Well, the action starts right away, and it's totally different at each electrode. And wow, the contrast is pretty stark. Over at the positive anode, we see fizzing. Bubbles of gas are forming all over it. But at the negative cathode, something completely different is going on. We start to see this pinkish metallic solid coating the surface. So, what are those bubbles? It turns out it's oxygen gas. The hydroxide ions that are already in the water get pulled towards that positive anode. There, they give up their extra electrons, that's the oxidation, and they reform into water and oxygen gas. Those electrons then flow out and into our circuit.
And that pink coating? That's pure copper. The positively charged copper ions swimming around in that blue solution are drawn to the negative cathode. When they get there, they pick up a couple of electrons, that's the reduction, and turn into solid copper atoms, plating themselves right onto the electrode.
Now, this has a really cool side effect that you can see with your own eyes. Since we're pulling all those copper ions out of the solution and turning them into solid metal, the solution itself starts to run out of them. And what gives the solution that vibrant blue color? The copper ions. So as they disappear, the blue color starts to fade away.
Okay, let's move on to case number 2, because this is where things get really interesting. We're going to swap out those inert graphite rods for active copper electrodes. This time, the electrodes aren't just going to sit on the sidelines. They are going to be major players in the reaction.
Now, a quick pro tip here. If you're using active electrodes and you want really accurate results, prep is everything. You got to clean them with some emery paper to get any gunk off, rinse them with water, and then use something like propanone to get rid of any oils from your fingers. This gives you a perfectly clean surface for the chemistry to happen.
So we're using the exact same circuit and the same blue solution. All we've done is swap the electrodes. We turn on the power. So do we see the same thing? Bubbles and a pink coating? Well, not quite.
The cathode looks pretty familiar. It's still getting that fresh coat of pink copper and gaining mass. But check out the anode. There are no bubbles at all. Instead, the anode itself seems to be dissolving, just shrinking away and losing mass as time goes on. And here is the big reveal. Instead of the water reacting, the copper atoms of the anode itself are getting oxidized.
The anode is literally dissolving into the solution, releasing fresh copper ions and sending its electrons off into the circuit.
Meanwhile, over at the cathode, it's business as usual. It's doing the exact same thing it did in our first case. Copper ions from the solution arrive, gain electrons, and deposit themselves as solid copper metal. Same reduction reaction, plain and simple.
And this creates this beautiful, elegant cycle. For every single copper ion that gets taken out of the solution at the cathode, a brand new one is put back into the solution from the anode. This means the concentration of copper ions stays exactly the same, so the solution stays that same vibrant blue. It's like a perfect little copper shuttle service. Okay, let's bring this all together. When you put these two cases side by side, you see the core lesson of this entire experiment. This is the aha moment, where it all just clicks.
Just look at this, side by side. The cathode reaction is our constant. It's always depositing copper, no matter what. The real story, the big difference, is what's happening at the anode. The type of electrode you choose acts like a switch. Flip it to inert, you get oxygen gas. Flip it to active, and the anode itself dissolves. And that one single change is what determines everything else, even whether the blue color fades or not.
And don't forget, this isn't just about some abstract theory. When you run this experiment, you're mastering some serious hands-on lab skills, from building circuits to making super precise measurements. But most importantly, you're learning how to connect what you can see with your own eyes to the invisible dance of atoms and electrons. So just remember, this is not just some quirky classroom experiment. This exact same process is used on a massive industrial scale to purify copper and to electroplate everything from jewelry to fancy car parts. It all comes down to this one idea: controlling the deposition of metal literally atom by atom. It makes you wonder, right? Where else could this kind of precise control change our world? What else could we build layer by layer just by harnessing electricity?